In the last video, we learned how to find the value lambda in the equation, in the characteristic equation, ax equals lambda x. And it turned out that we didn't need to know what x was. We didn't need to know the eigenvector in order to determine the eigenvalue. For example, if I have a matrix A that equals -4, -6, 9, 11, then in order to find lambda, I need to compute the determinant of the matrix A minus lambda I, where I, in this case, because A is a 2 by 2 matrix, I is the 2 by 2 identity matrix. And that is going to be the determinant of A, which is -4, -6, 9, 11, minus lambda times the identity matrix. Well, the identity matrix is going to be a 2 by 2 matrix, and the entries will be 1, 0, 0, 1. And when I multiply that by the scalar lambda, I get lambda 0, 0, lambda. When I do this matrix subtraction, which I can do because these matrices are the same, have the same dimensions, I get -4 minus lambda, -6 minus 0, 9 minus 0, and 11 minus lambda. And the determinant of that is -4 minus lambda times 11 minus lambda minus the product of these two entries, which is -54. So I will ultimately have plus 54. And that, let's see, I get -4 times 11 is -44. -4 times negative lambda is plus 4 lambda minus 11 lambda plus lambda squared, and then I have my plus 54. I'll put that into standard form, which has the terms in descending order of power. I get lambda squared minus 7 lambda plus 10. And that factors, let's see, I have lambda here and here. 10 is 2 times 5, 7 is 2 plus 5. So I have a 2 and a 5, and they are both negative. So the spectrum of A is the set 2, 5. Those are my eigenvalues for the matrix A. Now, I didn't need the eigenvectors to find the eigenvalues, but I do need the eigenvalues to find the eigenvectors. And here's basically why that's the case. We computed this formula, or we derived this formula, if you will, from messing around with this thing here. We introduced the I, and we decided that x couldn't be the zero vector. And so since it was in sort of factored form, I don't know if you remember that, we had this equation. We had a minus lambda I times the vector x was equal to the zero vector, and that told us that either x was the zero vector or this thing here had to be equivalent to the zero vector. Well, x being the zero vector is the trivial case, and it doesn't tell us anything. Right? A zero vector has no magnitude, and it doesn't tell us direction. So we can just ignore that case, and we're only focusing then on this case. And this does not have an x in it. We don't need the eigenvector x to determine lambda. But we do need the eigenvalues to determine the eigenvectors. So let's go back to that equation. A minus lambda I times the vector x equals the zero vector. And now that we have some values for some eigenvalues, we can take each one in turn and replace it in this equation. So I'm going to do just that. I'm going to rewrite matrix A as a matrix. I'm going to rewrite lambda I as the identity matrix with one of the two values in it. I'm going to rewrite x as a vector, and I'm going to rewrite 0 as a vector. So I'll get a, which is -4, -6, 9, and 11, minus I will be a 2 by 2 matrix, and when I scale it by lambda, instead of 1, 0, 0, 1, I get lambda 0, 0, lambda. I'm going to multiply that by a vector whose entries I don't know, but I know are distinct real numbers, so they may not be distinct. They may be the same, and that equals the 0 vector. And this arithmetic gives me -4 minus lambda, -6 minus 0, 9 minus 0, and 11 minus lambda. That is just the result of that matrix subtraction there. Try to tidy this up a little bit. That is not an x. Okay. I'm going to do some matrix multiplication to get this result. I'm not going to actually do the multiplication, but I've represented it here. And now I'm going to use, let's see, I'll use a highlighter and I'll go with yellow. I'm going to use the value of 2 for lambda. So in this last line here, everywhere I see a lambda, I'm going to replace it with a 2. And that gives me -4 minus 2 and 11 minus 2. And this, remember, is just a system of equations. I can do this matrix multiplication now, and I get -6x1 minus 6x2 equals 0, and 9x1 plus 9x2 equals 0. And if I solve one of these, let's just take this one over here. And if I add 6x2 to both sides, I get -6x1 equals 6x2. And let's divide both sides by +6. I get -x1 equals x2. So x2 can be written as -x1, which means that my vector x1, x2 is really just x1, -x1. And I can factor an x1 out of that. So I get 1, -1 times x1. And so I have here, it's kind of hard to see because I've written it so small, a vector that corresponds, I've highlighted it in yellow because the eigenvalue I used to get it is highlighted in yellow. This is the vector that corresponds to the eigenvalue of 2. So this is one of the eigenvectors for A. And of course, we could do the same thing with the 5. And in fact, I think I will. I'll go ahead and do the work for the eigenvalue of 5, but I'm going to need to do that on a new screen. So let's see, what am I going to need to copy over there? Really, probably all I need is this line here, because then I'm going to replace lambda with 5 and carry on from there. So I'll copy this line onto another screen, and then we'll go forward from there. Okay, here's my my working line again, and I had the spectrum of A was 2 and 5, and I'd already worked out that the eigenvector for 2, there's the eigenvalue, the eigenvector was 1, -1. So there's one eigenpair. And the other will be 5 and some eigenvector. And so what I'm going to do now is replace these 5s, sorry, these lambdas, with 5s instead of 2s. So I get -4 minus 5, which is -9, negative 6, 9, and 11 minus 5, which is 6, times the vector x equals the 0 vector. When I do this matrix multiplication, I get negative 9 times x1 minus 6 x2 equals 0, and 9 x1 plus 6 x2 equals 0. Choose either of those and solve for one or the other of the variables. And let's see, I'll factor out, no, I'll just add 6 x2 to both sides. So I get negative 9x1 equals 6x2. And then I want to write x2 in terms of x1, so I'm going to divide both sides by 6. And I get that x2 is equal to negative 3/2 x1. So that means that my vector x1, x2, right, this is the thing we're just calling this x, but this is it in its sort of expanded form. This is equal to x1, and x2 could be written as negative 3/2 x1. So I have, if I factor out an x1, I have a 1 and a negative 3/2. So my other eigenvector down here is 1 and negative 3/2. So we have found here, on the previous screen we found an eigenvector for the eigenvalue of 2, and here we have found an eigenvector for the eigenvalue of 5. But it's important to recognize that these eigenvectors are not unique, because an eigenvector is by definition a scalar multiple, any scalar multiple of the result you would get by multiplying a matrix by some vector, right? If you multiply a matrix by some vector and you end up with any scalar multiple of that vector, then that vector is an eigenvector. And that scalar multiple can be any number. So for example, another eigenpair would be 2 and negative 3, 3, right? This is another eigenvector for A for the eigenvalue 2. So they're not unique. You may do, if you solved this for x1 and wrote x1 in terms of x2 instead of the other way around, you'd get a different eigenvector